Alright guys, for experiment 5, reduction of unknown aldehyde and ketone experiment, we're going to review mainly two things. Firstly, the mechanism of the reaction, and then the differentiation of using sodium borohydride and lithium aluminum hydride as a reducing reagent. Okay, right. Firstly, let's talk about mechanism, or basically what happened after you add in, sodium borohydride into your unknown solution. Well, we used ethanol as a solvent for the reaction, right? The reaction will also proceed if you use methanol as the solvent. Right, so what you observed after adding sodium borohydride into the solution mixture is the bubble. We know that to produce bubble, you're creating a gas, and in this way, the gas that's being produced will be hydrogen gas, right? Which is the only gas that makes sense. Well, the valence of hydrogen gas was a 0 because it's a diatomic molecule, and it's combined by the donation of a +1 proton and a -1 hydride, right? So we're going to be writing out what's left from the solution. OCH2, CH3. And it doesn't stop here. As a matter of fact, the hydride are going to be replaced by the ethoxy group, which lead you to produce, let's write it out, 3 hydride are going to be replaced. OCH3, and give you the byproduct. It's called sodium triethoxy hydroborate. And this reagent are going to be acting as a reducing agent of this reaction. Because it's a stronger reducing reagent compared to sodium borohydride, it have a very bulky group, which makes the hydride very easy to be kicked off or to attack as a nucleophile. And then let's write it out in a mechanistic form, in a stepwise manner. We'll use acetone as a example starting ketone. It will be the same case if you started with an aldehyde. Well, we know the hydride will be the nucleophile, right? And hydride will be the species that's gonna do the attack. That's the hydrogen we add here. At the same time, it's gonna kick the double bond. It's gonna shift one of the double bonds, the electrons up to the oxygen, which created an alkoxide intermediate. Since we're going to be producing a propanol in the end, so your alkoxide has to be protonated somehow. You may use water. There are a small amount of water. You can also use ethanol, which is in excess, to do the protonation, which lead you to the product of the final alcohol. You can also use sodium borohydride here to write the mechanism, although it's not as accurate, since the sodium triethoxy hydroborate will be the reducing reagent. All right, the next thing we're going to discuss will be, I'm sorry, I forgot to add a photo. Let's try if I can still add a photo. There it is. Perfect. Add. Nice. Hey, where's the second one? Alright, so the two photos I'm going to show you will be the comparison between using lithium aluminum hydride and sodium boron hydride as a reducing reagent on the various kinds of starting materials. Some of these will be tested in either lab final or quizzes. Some of those already are. You will need to know the difference between these two reagents and how they were used, and to which extent it's going to reduce its starting materials too. Okay. So firstly, sodium boron hydride is not as strong as lithium aluminum hydride, which can reduce a variety of compounds. However, sodium boron hydride, which is the one we use today, is a rather gentle reducing reagent, or relatively gentle. It will work with ethanol or methanol, protic solvent. As long as you avoid strong acid, you should be fine. And mainly, it will reduce aldehyde or ketones to primary or secondary alcohols. The reaction produces hydrogen gas as a byproduct, and the neutralization or extraction are rather simple. It's also going to create there's a possibility it's going to create an enantiomer as well, since the reduction was not stereoselective at least. So remember that when you're writing out a reduction equation, you can possibly be creating two enantiomers. So make sure you list both structures out. Okay. If you use lithium aluminum hydride, then you will need to be a lot more careful, since it's a pretty strong reducing reagent. It will react with many of the known compounds you use, for example, ethanol. For example, methanol. They're going to react very violently, which is why you cannot use ethanol or methanol or any protic solvent as together. Ether or THF are normally the preferable solvent for lithium aluminum hydride. And of course, you would also want to avoid strong acid, halogenated compound, or alcohols or amines, because it will react with all of those. Then let's talk about how they will react. Well, similarly with sodium boron hydride, it's going to reduce aldehyde and ketones into alcohols. These are the same, right? However, when coming to esters, sodium boron hydride wouldn't work on esters. However, lithium aluminum hydride can reduce that to alcohols. And the reaction goes oxygen O2. I'm sorry, that's not an ester. OCH3. If you use lithium aluminum hydride, what's the product? You're actually going to cleave it here, right? And CH3OH, is that it? No, because your acid can also be reduced by lithium aluminum hydride, right? Lithium aluminum hydride, which means that it's going to be reduced to OH and methanol, all the way to the alcohol, right? That's what the lithium aluminum hydride will do. And your sodium boron hydride will not be influenced by or will not react with an ester. How about an epoxide? Well, here there's an epoxide to alcohols. So you start with epoxide. The hydride will attack and open the ring, which will also lead to the formation of an alcohol, right? As we mentioned, epoxides are very reactive. They can be opened with either acid or base. Of course, they are going to be subject to lithium aluminum hydride reduction. And we have nitriles and amides. There are slight difference. using nitrile or amide, although you stop at amines. Let's see, for a nitrile, you're gonna go to NH2, right? Is this correct? Not really. See, you have 1 carbon, 2 carbons, and here you only have 1 carbons, right? Always be careful when you're writing out an equation or a structure, count the carbons. Sometimes students will tend to lose 1 or 2 carbons during the completion of a line reaction. If I were you, I would label out carbon 1, 2, 3 and make sure they are the same number after you finish with the reaction. Same case with amide. We'll use this as example, lithium aluminum hydride. Lithium aluminum hydride. I have 1, 2 carbons and the nitrogen, right? Well, 3. In the end, I should have 3 carbons. And the size that's being reduced will be the carbonyl, right? The same case as when we're writing out the other reaction. So, well, it's going to lead to an amine. Here's an amine. And let's see, 1 carbon, 2 carbons, and 3 carbons, right? So it doesn't matter whether you started with the amide or nitrile, you're going to have an amine product in the end, okay? Well, in the end, it says if you start with a halide, it's going to react it or reduce it to an alkane. An example will be Cl or bromo, lithium aluminum hydride. Well, you can't lose a nitrogen or you can't lose a carbon, right? So it's going to be an ethane. Let's see, RCH3, right? So this is going to be the alkane product after the reduction of using lithium aluminum hydride. If you want to have a detailed comparison, here's a table summarize everything you need to know about lithium aluminum hydride. All right, last but not the least, let's pick out the reaction that can be enabled by sodium borohydride. We know aldehyde can, we know ketone can, right? Ester, no. The rest, no. This one, definitely no. Acid, no. Right? So be very careful which reagent you use and what is the final product you will get. And also be careful about stereochemistry.